Hello, I'm Henry Toczyk, the founder of Dairyland Electrical Industries. This presentation deals with close interval surveys conducted on decoupled pipelines. By decoupled pipelines, I am referring to pipelines where the decouplers have been connected between the pipeline and a grounding system, a common practice to minimize induced AC voltage on a pipeline, to provide AC grounding for electrical equipment in a pipeline, such as a motor-operated valve, and other similar applications. The reason for this presentation is to make more people in the corrosion industry aware that decouplers may affect the potential measurements obtained during a close interval survey. I will provide information on how to determine if a measuring problem exists, why it occurs, and actions to take if it does occur. First, some background information may be helpful. Several years ago, one of our customers called and asked why they were getting unrealistically high off potential measurements when conducting a close interval survey on a decoupled pipeline. In this case, the user was obtaining potential measurements that were too electronegative to be realistic. The problem is that such measurements make a pipeline appear better protected than it really is, when in fact it might not be adequately protected. At that time, we did not have a definitive answer as to why this problem was occurring. We discussed this question with other knowledgeable corrosion engineers, and no one had an explanation, just various opinions as to what the reason for these high potential measurements might be. To determine the cause of this phenomenon, we hired and worked with people from two different highly respected corrosion engineering firms to assist us in determining the cause of these high potentials. To determine the cause, measurements were taken on an actual pipeline in the field where this measuring issue was present and at a pipeline test site. Similar measurements have since been taken on a number of other pipelines to gain more information. With the background information just provided, let's take a look at a waveform taken during a close interval survey that exhibits the problem just described. The above waveform shows that at the instant of current interruption, there is an immediate voltage drop from 2.1 to 1.8 volts, or 300 millivolts, followed by what looks like rapid depolarization, which could occur in an oxygenated environment. The real clue that something is wrong here is that an off potential can theoretically not be more than minus 1.2 volts when measured with respect to a copper sulfate half cell, commonly shown in the literature as a capital letter V with a subscript CSE. If the off potential for this waveform were measured at a typical 300 millisecond measuring delay time after current interruption, the off potential of about minus 1.8 volts would certainly indicate that something is wrong, since it is significantly greater than the minus 1.2 volt limit. If you obtain an off potential waveform that looks similar to the one shown above, including wide variations of this waveform, you will not obtain an accurate off potential. This waveform was recorded at a valve site in a pipeline 500 feet from two decouplers. To confirm that the previous waveform was due to the decoupler, this is a waveform taken on the same pipeline and at the same location, but with the two decouplers disconnected. Under this condition, one obtains a waveform on which an accurate off potential can be taken, because the voltage quickly reaches a stable off value and it is not more negative than the minus 1.2 volt theoretical limit mentioned in the previous slide. When conducting a close interval survey on decoupled pipelines, it is good practice to first examine an off waveform with a long on-off cycle, say on the order of 7 seconds on and 3 seconds off, because the resulting waveform will clearly show if the off potential has reached a stable level at the time the off potential measurement is normally taken. Usually the off measurement is taken 100 to 300 milliseconds after the rectifier current is turned off, a time commonly referred to as the measuring delay time. On many pipelines, this waveform will readily show that an accurate off-potential measurement may not be accurate at the normal measuring delay time used, but may be accurate if the measuring delay time were increased. To understand why decouplers may affect close interval survey off-potential measurements, it is necessary to understand the basics of a cathodically protected pipeline and how these measurements are taken. This slide shows a schematic representation of a pipeline that is cathodically protected with an impressed current system. Cathodic protection is provided by the rectifier labeled V sub R and an anode bed with a resistance to earth R sub A to remote earth. The switch S1 represents a switch that can interrupt the current from the rectifier with a pre-selected on and off time. On the right side of the schematic, inside of the dashed blue box, are the basic pipeline parameters. R sub L and L sub L represent the pipeline longitudinal resistance and longitudinal inductance. A pipeline also has a shunt impedance across the pipe-to-soil interface consisting of the shunt resistance through the pipeline coating labeled R sub S, which is in parallel with a shunt capacitance labeled C sub S. The E sub S term represents the voltage across the coating capacitance due to polarization. This shunt impedance is in series with the resistance of the coated pipe to remote earth labeled R sub P. E sub P represents the corrosion potential of the steel pipe with respect to the soil. The magnitude of this pipe steel potential is typically minus 0.6 volts when measured with respect to a copper sulfate reference electrode, which is the normal reference to which corrosion potentials are measured. When the rectifier is on and the switch S1 is closed, DC cathodic protection current flows from the anodes through the earth to the surface of the pipeline, causing the pipeline to polarize. The term polarize simply means that a potential is developed across the pipe-to-soil interface that tends to oppose the flow of current, as represented by the charging of C sub S to a voltage designated by E sub S in the schematic. I have taken some liberty with the normally used subscripts for some of the terms in an attempt to simplify them. Next, let's review the requirements for a pipeline to be cathodically protected. According to NACE criteria, one of the two conditions listed on this slide must be met. The above terms were described on the previous slide except the term labeled E with the subscript CS, which pertains to the 100 millivolt shift criterion. Of these two criterion, the more commonly used with modern high-resistance pipeline coatings is the minus 850 millivolt polarized potential criterion, which is a measurement typically taken within a fraction of a second after the rectifier current is switched off. Measuring minus 850 millivolts with respect to a reference electrode with the rectifier current on is not the same as the polarized potential criterion, because a potential measurement with the rectifier current on includes a voltage component commonly referred to as an IR drop error term. The 100 millivolt polarization shift criterion is most commonly used on pipelines in high resistivity soils or on poorly coated or bare structures where it is difficult or impossible to achieve the minus 850 millivolt polarized potential criterion. However, to determine if the minus 100 millivolt shift criterion is met, it is necessary to conduct two surveys, an off-potential survey and a depolarized survey. To do this, the rectifier is left off for a period of time, sometimes weeks, to allow the pipeline to depolarize completely, after which a close interval survey of the pipeline potentials are taken. The corrosion potentials on the depolarized pipe are then compared with the polarized potentials to determine if a minus 100 millivolt shift is obtained at all points along the pipeline. When decouplers are used on poorly coated structures or poorly coated pipelines and close interval surveys are conducted, the measuring error under discussion does not normally exist because such pipeline circuits have a very low RC time constant, which will be explained later. A pipeline is considered adequately protected if the 100 millivolt shift criterion is met, even though the minus 850 millivolt criterion may not be met. This slide shows a simulated potential measurement being taken between the pipe and a copper sulfate reference electrode placed on the ground above the pipeline with the rectifier current on, highlighted in blue on this slide. In practice, the closest one can place the reference electrode to the pipe is to place it directly above the pipe in contact with earth. The problem with the resulting measurement is that cathodic protection current passing through the soil between the reference electrode and the surface of the pipe coating will produce a voltage drop, which is the product of the rectifier current flowing through the resistance labeled R sub P in this slide. When the voltage drop through the soil between the reference electrode and the pipe is included in the measurement, it makes the pipe appear to have a more electronegative potential and to appear better protected than it really is, because this voltage component does not contribute to cathodic protection of the pipe. To get at the true polarized potential, it is necessary to eliminate this ICP R sub P voltage drop component from the measurement because it is an error term, commonly referred to as IR drop error. The next question is, how is this IR drop error component eliminated from the measurement in order to obtain the true polarized potential of the pipeline? This is normally done by switching off the rectifier current and then quickly taking a potential, which then eliminates this IR voltage drop error component. In practice, since a transient voltage can occur the instant the rectifier current is turned off, the potential measurement is normally taken several hundred milliseconds after the rectifier current is interrupted to avoid measuring this potential voltage spike, which would introduce another error. The top graph shows the current being interrupted at a time t equals 0, and the bottom graph shows the off potential measurement being taken at t equal 250 milliseconds, a typical measuring delay time. The difference between the on potential and the off potential is the IR voltage drop error component that was eliminated. This illustrates the difference in potential when measured with respect to a reference electrode with the rectifier current on, which includes the IR drop error component, and with the rectifier current off, which excludes this error component and represents the polarized potential of the structure. Had this error term not been eliminated, the pipeline would appear more electronegative and better protected than it really is. All off waveforms will not look like the ideal example shown in this slide. Next, I am going to expand a pipeline schematic to include a decoupler. This example represents a typical application, such as where a decoupler is connected between a pipeline and a bare grounding system, typically zinc or copper in an AC voltage mitigation application, or just copper if providing AC grounding of electrical equipment in a pipeline. The new circuit elements that have been added are the capacitance of the decoupler, labeled C with a subscript D, a grounding conductor which has a corrosion potential of E sub G. This grounding conductor has a resistance to remote earth represented by R sub G. Under normal operating conditions with the rectifier current on, you will note that there is no DC current flowing in the right leg of the circuit because the capacitor in the decoupler blocks the flow of DC current. When a decoupler is first connected to a pipeline with the rectifier current on, there will be a very momentary current flow to establish a voltage across the decoupler, labeled E sub D, in order to make the voltage on each side of the equation equal. This equation represents the voltage across each element in each leg of the circuit. The sum of the voltages across each leg of the circuit must be equal since they are in parallel, a fundamental principle of electric circuits. This slide is key to understanding how decouplers can contribute to excessively electronegative potential measurements. So bear with me until the next slide, which will summarize the essence of this slide. When the rectifier current is interrupted to take an off potential measurement, one would expect the pipeline voltage to decrease in value because the IR voltage drop component, highlighted in orange in the left side of the equation, was eliminated. However, since each side of the equation must always be equal, this means that the voltage across the decoupler capacitor, represented by E sub D, must then change exactly by the value of the IR drop component that was eliminated by turning off the rectifier current. The voltage across the decoupler is the only element in the right leg of the circuit that can change in voltage to keep the voltage across the two legs of the circuit equal, since the corrosion potential of the grounding conductor, E sub G, is fixed in value. These two parallel circuit legs consist entirely of resistive and capacitive elements, and such circuits are referred to as RC circuits. Whenever DC current is flowing in an RC circuit and that current is interrupted, the voltage across energy storage components in the circuit, such as capacitors, cannot change instantaneously in voltage. The voltage across such energy storage elements can only change at a rate determined by the RC time constant of the circuit. To effect the required change in voltage across the decoupler, and therefore a change in the pipeline voltage, a transient current automatically begins to flow the instant the rectifier current is interrupted to cause the required change in voltage across the decoupler and to reduce the pipeline voltage to its polarized potential. The time that it takes for this voltage change across the decoupler to take place depends on the resistance and capacitance values of the circuit, which can vary considerably between pipelines. Key factors are the resistance of the pipeline coating, the capacitance of the decoupler, and to a lesser extent the capacitance of the pipeline, the number of decouplers installed and their spacing, the pipeline length and diameter, which affects both the pipeline resistance and capacitance to earth. It takes about 5 RC time constants for the transient current to fully dissipate and for the pipeline to reach its final off potential. Any measurement taken before this transient current has dissipated will result in an off potential measurement that is excessively electronegative because there will still be an IR drop error component that is being caused by this transient current flowing through R sub P. A decoupler manufacturer has no control over the resistance or R part of the RC time constant and a very limited control over the capacitance or C part. Before the rectifier current is interrupted to take an off measurement, the voltage across the decoupler will be different if the grounding conductor is zinc versus copper, all other factors being equal. However, the voltage across the decoupler must still change by the same value of the IR voltage drop component that was eliminated by turning off the rectifier current, and it takes the same amount of time independent of the grounding conductor material used. In some cases, the decoupler capacitor may need to be discharged and in other cases charged to effect this voltage change across the decoupler. In the above schematic, I show the case where the capacitor is being discharged to effect the required voltage change. An understanding of this slide is key to understanding why an off potential measurement can exist on some decoupled pipelines. To try and simplify the long explanation of this measuring error phenomenon given in the previous slide, This slide provides a condensed explanation which gets to the heart of the issue. When rectifier current is interrupted to take an off potential measurement, the voltage across the decoupler must change by the value of the IR voltage drop component that was eliminated by turning off the rectifier current. To effect this change in voltage across the decoupler, a momentary transient current will flow automatically to effect this voltage change. Until the voltage change across the decoupler is complete, this transient current will cause an IR drop error that is due to the transient current flowing through the resistance R sub P. A potential measurement taken before this transient current has dissipated will result in a potential measurement that is too electronegative. An obvious question is, what brought this measuring issue about, since it was not mentioned by any customer until nearly 17 years after solid-state decouplers were first introduced? Since solid-state decouplers were first introduced to the corrosion industry by Dairyland Electrical Industries, many new pipelines have been installed with improved pipeline coatings, and old pipelines with lower resistance coatings were retired, thereby increasing the overall pipeline resistance to earth, which increases the R and the circuit RC time constant. A second factor is the recognition in recent years that voltage has to be mitigated to lower levels in low resistivity soils to minimize AC corrosion. This is often done by installing lower resistance AC mitigation grounds and more decouplers along a pipeline that is affected by induced voltage. The capacitance value of the decouplers furnished by Dairyland has been the same since they were initially introduced, so they did not contribute to a change in the circuit RC time constant. But added decouplers in parallel do increase the C in the circuit RC time constant because the capacitance values of decouplers in parallel are directly additive. A third factor is that when decouplers were first introduced, potential measurements with the rectifier current off to determine the true polarized potential were not that commonly taken. Since that time, regulators have put increasing pressure on taking off potential measurements due to a number of notable pipeline failures due to corrosion. At this point, some may ask, why use decouplers if they contribute to this measuring issue? The basic reason is that solid-state decouplers have solved far more problems than this one measuring issue they contribute to on some pipelines. The maintenance-free solid-state decouplers have been a significant contribution to the corrosion industry in that they have addressed a number of key issues as noted on this slide. Since this instant off measuring issue was identified and understood, varying decoupler designs have been evaluated with alternate characteristics and varying capacitance levels. From work done to date, simply lowering the decoupler capacitance is not the solution because to make the capacitance low enough to eliminate this possible measuring error on most pipelines creates other problems that are even more difficult to address. So how does one determine if an instant off CP measurement on a decoupled pipeline is likely to be in error? To answer this question, it is recommended that one plot, record and analyze an off waveform with a longer than normal on-off cycle, such as 7 seconds on and 3 seconds off, for example, and sometimes even longer. This waveform will readily show whether the off voltage is stabilized at the time delay normally used to take an off potential measurement. If it has not stabilized by that time, determine whether one can increase the measuring delay time and take an off measurement after the off voltage has stabilized due to the transient current being dissipated. If feasible, then increase the measuring delay time accordingly to obtain an accurate measurement, as this is the simplest solution. For example, a waveform may show that an accurate measurement is not possible with a 250 millisecond measuring delay time, but is possible if taken with a longer measuring delay time. Measuring delay times well over 1,000 milliseconds have been used to obtain accurate measurements, but longer times can be used. When increasing the measuring delay time to obtain an accurate CP measurement is not feasible, then other means must be used to obtain an accurate potential measurement. I suggest reviewing this slide carefully because it represents several key aspects of this off potential measurement issue. This slide shows an off waveform on a 6-inch, 40-mile long pipeline using a long on-off cycle to illustrate the effect of a pipeline circuit with a long RC time constant. This specific pipeline had multiple decouplers installed. If an off potential measurement were taken at a typical 200 to 300 millisecond measuring delay time with all decouplers installed, as illustrated by the magenta waveform, the potential measured would be significantly too electronegative relative to the potential with no decouplers installed, as represented by the black waveform. On this pipeline, with the on and off cycle time shown, one cannot obtain an accurate off potential measurement with all decouplers installed because the off voltage has not stabilized even after 2.4 seconds. However, in this case, if the off time had been increased to whatever time it took for the voltage to stabilize and a potential measurement were taken and found to be at least minus 0.85 volts, the pipeline would be adequately protected even if depolarization were occurring at that time. It is only if the potential were not at least minus 0.85 volts that additional testing by other means would be required to determine if the pipeline were adequately protected. While such long on and off times would greatly slow down the process of taking a close interval survey, it is an option to consider. The higher the resistance of the pipeline coating and the shorter and smaller the diameter of the pipeline, the higher the resistance to earth and the higher the R and the RC time constant. This is because there is less surface area of coating in contact with earth. Conversely, larger diameter and longer pipelines will have a lower resistance to earth due to more surface area of coating in contact with the earth and therefore a lower RC time constant for the same coating resistance. Similarly, the contribution of the pipeline capacitance to the C part of the RC time constant will vary with pipeline length and diameter, but is opposite that of the resistive component. That is, the capacitive contribution of the pipe coating increases with longer and larger diameter pipes and decreases with shorter and smaller diameter pipes. This pipeline capacitance adds directly to the decoupler capacitance in the circuit RC time constant. For the example shown, the pipeline capacitance was determined to be approximately 14% of the total circuit capacitance on this rather small diameter pipeline, but will be considerably greater in larger and longer pipelines. This is an example of an off waveform on an extremely short, small diameter pipe at a pipeline test site where an off waveform was recorded with and without one decoupler installed. When decoupled, it took about 1 second or 1,000 milliseconds for the pipeline to reach a stable off voltage. In this case, an accurate off reading could be taken with about a 1 second measuring delay time. This measuring error has not been an issue on coal tar coated pipelines in the field because those pipelines are considerably larger in diameter and longer in length with a lower RC time constant. But this example shows that this measuring issue can still occur with lower resistance coatings if the pipeline is very small in diameter and very short in length. Similar measurements were taken at the same pipeline test site on a 2-inch diameter, 250-foot long pipe that was FBE coated, and the circuit RC time constant was many minutes long, thereby preventing any off potential measurement by increasing the measuring delay time which is an extreme worst-case example. In the above waveforms, the ripple when the rectifier is on is from the rectifier and from noise when the rectifier is off. Assuming an off waveform with a longer than normal on-off time shows that an accurate off potential measurement cannot be obtained by increasing the measuring delay time, what are other options for obtaining an accurate potential measurement? This slide illustrates options that have been used, not listed in any order of preference. Some have installed interrupters in series with each decoupler when relatively few decouplers are involved, as this gives accurate off potential measurements because it eliminates the decoupler capacitance value entirely. Others have chosen to install an isolation switch in series with each decoupler to easily disconnect the decouplers during the time a close interval survey is being taken. With either the isolation switch approach or installing an interrupter in series with each decoupler, the user should take safety precautions if the decouplers were used for AC voltage mitigation, because the voltage on the pipeline could rise above the maximum 15 volts allowed by NACE when all decouplers are disconnected. Based on field testing done by Dairyland, it is not necessary to disconnect all decouplers on some pipelines in order to obtain an accurate potential measurement, though an increased measuring delay time will likely be required. By leaving some decouplers installed with sufficient spacing between them, the voltage may be kept to safe levels with accurate off potential measurements still possible. Due to the many variables involved, it is not presently possible to provide definitive guidelines as to the minimum decoupler spacing along a pipeline that may enable accurate off potential measurements due to the many variables installed. This method can be combined with the isolation switch option because it may allow most decouplers to be disconnected, thereby enabling an accurate potential measurement while still limiting the pipeline voltage to a safe voltage level. Using IR-free coupons is another option, but they do not provide potentials all along the pipeline as is required in a close interval survey. This is a photo of a Dairyland isolation switch installed to a Dairyland PCR model decoupler in a pedestal. This switch is being used by some companies to make it easy to disconnect and then reconnect the decoupler for purposes of taking close interval survey measurements. Although the PCR is certified for Class 1 Division II hazardous locations, when the switch is installed, the pedestal and decoupler must be in a non-hazardous location because the switch is not certified for use in hazardous locations. Most AC voltage mitigation applications where decouplers are installed would not normally be a hazardous location. An isolation switch version is also available for Dairyland SSD model decouplers installed in a pedestal, and there is an isolation switch version furnished complete in its own enclosure for use with decouplers that are not installed in pedestals. So what can be concluded from what has been learned to date? It is now known that instant off potential measurement errors exist on some decoupled pipelines, and the reasons for those errors is now understood. These measuring errors were brought to light due to more pipelines in service with higher resistance coatings and increased levels of AC mitigation to prevent AC corrosion, which generally involves more decouplers along a pipeline. These two factors increase the RST time constant of the pipeline circuit, which can adversely affect instant off potential measurements. Further field testing by Dairyland indicates that the decoupler capacitance cannot be reduced to a low enough value to eliminate this measuring issue on many pipelines where this measuring error exists. Where a measuring error exists as determined by waveform analysis, first consider an increased measuring delay time if feasible. If not feasible, then one of the various alternative means mentioned should be considered to obtain accurate potentials. Work continues toward a solution to this measuring issue, including work toward a potential alternative measuring solution to obtain an accurate CP measurement without the IR drop error component. However, at this time, the most common measuring options available are those mentioned in this presentation. DEI acknowledges the major contributions of corrosion service and Gull River engineering to understand the causes of erroneously high potential measurements obtained on some decoupled pipelines during close interval surveys. A special thanks to Rob Wakeland of Gull River Engineering for his review and assistance in editing this video presentation. But thank you for the time to watch this video today. It is a very detailed topic. If you have more questions or would like to discuss this further with an engineer, we are always available to help.